Good morning. So let's continue with numerical PDEs. So since we stopped, let me do a quick revision of what we saw. So unidirectional, right? One direction. So we saw many things. So we saw numerical diffusion. We saw numerical I was using epsilon. Okay, depending on the method, and this is something you're doing on the computer, so it's quite nice to see that we study this through the modified equation. Okay. And and actually part of the exercise, right, was to see, so let me call this maybe A, B, and to see that A, right, if you have something like a front coming like this, right, it will eventually, with the first method go like this. This is the numerical diffusion. And B, if you do the same problem, like this, it will be like this, the numerical dispersion. Okay? So, excuse me, let me do, which I think I did last class very quickly, and for some of you that were in the class here last time did numerical PDEs with me, did PDEs and applications with me, numerical PDEs is now, and also some of you are doing PDEs, another course of PDEs here at IMPA. Let me do this. Let me do a quick review . So let me do a very, very, very quick, like super fast, quick review of some things of PDEs, characteristics, because I want to mention next a numerical method of characteristics for you, okay? So some of you are doing right now that I know the PDEs course, which is the master's one. Have you seen this equation here, the quasi-linear, right? And you know the geometrical interpretation of this, right, as an inner product, okay? Which basically gives you, so let me put this to be complete for people who are watching. So if I have this as my integral surface, right? This is just an inner product, A, B, C, and the gradient of the surface. Okay, if I call this S, right, just putting it very quickly. And from this, we get the characteristic equations. Let's see the notation I'm using, tau. Okay, so everybody familiar with this? Right, so this is the inner product. See, this is basically the inner product. I'm writing this very quickly. This is just ux, uy, minus 1, the gradient. So that means here is the normal, which is the gradient. Okay, and this is the tangent field. Okay, and these are the characteristic equations. Okay, and so this is the notes, and then for let me go to the other board. If I'm using, so I'm doing this. Which is burgers. Here we have, let's see what I want to say here. Here we have the, I think I already did this last time, right? These are the characteristics. dx dt equals to c, okay? Looked at here, y is playing the role of time, this way, generic notation. And here, maybe I should put a different color, right? So you can see this 3 graph. Right, which actually means this, just x, t, information is flowing like this. And then here, it depends on the initial data, right? So let me put it like this. So if my initial wave is something like this, here it's going to go like this, here it's going to go like this, here it's going to go like this, and maybe we might have a shock. Okay? Everybody, I'm going very fast, but I think everybody has seen this somehow. Okay? Either you're seeing the PDEs course right now, you saw in PDEs of applications. In the notes, it's done in more detail, a little more detail, but there's the notes of the PDEs course. But this is just to remind us quickly of characteristics so that I can mention something in terms of numerical aspects of this. Okay? So, let's see what else I should say. So this is burgers. This is the wave equation we saw. Okay, so now one quick comment. I'm going to make comments now about, say, characteristics and also the method which is called semi-Lagrangian. Okay, so first note, let me call or facts. So I mentioned the first fact is related to burgers. So burgers, we can write it in 2 ways. Or okay, so this is called the conservative form. This is called the non-conservative conservative form. Okay, I'm going to talk, maybe not today, maybe next class, when we have systems, the non-conservative form, it's good because we have a matrix here, which is the flux matrix, and the eigenvalues of this flux matrix are of interest. We'll see this. Even if it doesn't make sense to you right now, don't worry. This part here is called the conservative form. So let me check with you. I know that some of you took the class with me with PDEs and applications. Some others take now. Do you know why this is called the conservative form? I mean, first, before I ask the question, mathematically, trivial. It's the same thing, right? Just take the product. Take the derivative of the product. Ridiculous, right? So mathematically, they're equivalent. Mathematically, they're fine if you have a classical solution. That means a solution that has a derivative. But it's different, I'll mention to you, if the solution is not classical, okay, is a weak solution. So question number one, go back to the question I made to you. Do you know why this is called the conservative form? No? Okay. The reason this is called the conservative form is that, and then like if you look at my notes, PD's notes, particularly ones, there's the one in English, whatever, you will see it's very easy. I'm not going to do it here, but I'm just going to mention that if you integrate both sides, but you're going to understand just in words, okay, which is good practice. If you integrate this, both sides, in terms of time, right, you're going to get, in space. I'm a little bit spaced out from the trip, so it's space. If you're going to integrate this in space, you're going to have the total mass of this guy, the derivative, and pull the derivative of time outside, you're going to get the integral, say in an interval AB. Okay, on purpose I'm not going to write it so that we exercise. So on an interval AB, I'm going to get the derivative of time of the integral in x from A to B of u. And that is usually called the total mass of u, even though if you're not doing fluid dynamics, even though if it's not mass. But in general, it could be mass, okay? So if then you integrate this in space from A to B, because of this derivative, it's going to be the value of, say, B minus the value of A. And that's why it's called the term related to the flux function, because it's telling you the flux of this quantity at the extremes of your interval AB. Okay? Now, if you put AB far enough, and you say there's nothing happening at the extremes, this is going to integrate to 0, because the flux at the extremes are 0, because the dynamics is just happening here. Therefore, d dt of the integral of u is conserved, the total mass of this quantity, right? Mass in the general sense, just like in probability, we say total mass 1, right, for the measure. So here the total mass of this guy, u integrated from A to B, is conserved in time because the integral of u, dt, is going to be equal to 0 because there's no flux on the boundary. If there is flux on the boundary, then instead of a conservation law, you have a balance law, even though usually we abuse of the word conservation because something is conserved in the sense that what's going out in the flux is balanced by the integral inside. Okay? So on purpose, I'm not going to write this because it's good if you don't fully understand. You look at the video and you refresh what I'm saying. Okay, it's really as an exercise. So this is why this form is called the conservative form. And this one, because the flux function is written like this, the non-conservative one is good because when this is a system, here we have a matrix, we can look at the eigenvalues. And when this is not a system like here, we see that the velocity of propagation is played by the solution. So it's trickier to see the speed at which things are propagating And that's why we see it here. It depends on the initial condition. It depends, it depends on this height. Okay? Now, a fact that I will not prove, it's usually, for this case, you can do it, there's a little bit of a cancellation, telescopic cancellation, but you can see it easily on the computer, is this. If you have these two guys here, which mathematically are the same, and you want to solve them on the computer with the same, basically the same numerical method, which one would you choose? And this is really not a fair question to you, because, and I'm not going to do all the details because you haven't seen it, and I haven't explained. It's just basically on your intuition, right? So the thing is, let me write the numerical method just as you think. And just looking at the numerical method, I wouldn't know how to answer the question if I hadn't never heard this question. So here it is. So the numerical methods would be like this. And there's an interesting problem that actually is in part of that introductory short course that I wrote. It's written in Portuguese. And the problem is like this. Okay, so here's a little simple problem that you find sketches in the notes, and this is actually in the notes of that introductory short course in the Brazilian meeting colloquium that I did with Esteban Tabac, who is an Argentinian friend and mathematician professor at Courant Institute, and he proposed this problem, and the problem is like this. So let me tell you the problem. So here is, going back to my introduction, right? Here is Burger's equation, written in two similar ways. Mathematically, what's the big deal? But I explained. One's conservative, the other one's non-conservative. Here is a numerical method, like an upwind type numerical method, right? This is just upwind, right? Upwind numerical method. So J minus 1, and N minus 1, okay? But I can discretize the above one like that, like this, the one below like that. Is there going to be a difference when I do it on the computer? Yes, or else I wouldn't be wasting our time here, right? And Esteban proposes this very nice, simple problem, really simple baby problem for what's called flood waves. So look at this problem, very cute, very simple, very cute. So I have a river. Okay, this sketch is a river. This is, say, the bottom of a channel. And it's a one-dimensional problem, okay? But this is just to indicate, so it's a one-dimensional problem, okay, in X. But this is just to indicate that the problem, which is usually equations like this are called shallow water equations. I might mention some of this later on, but of course we see this in detail in the PDEs and applications course. So this model is like this. U is called a wet cross-section. So the river, which is not always like this, is like more like a channel than a river, which is a rectangular cross-section. The river, the cross-section changes. And there's interesting mathematical problems related to that. But here, it's more like a channel, like a rectangular channel, boom. Cement, no penetration, right, impermeable. The water is flowing down. And what you model, so it's a model that you average it over the depth and over the sides. So it's a one-dimensional quantity, and it is the wet cross-section. So if there's a wave, this guy grows, right? Laterally, it doesn't change. Now there's this condition, there's this time-dependent boundary condition upstream. So this is a river. The river is flowing in this direction, right? It's a unidirectional wave equation. It's not raining, so it's a constant thing. And the river, of course, in this case, you can add, there are models you can add a current, but here, let's pretend there's no current. The river is just sitting there, okay? Then, this is the raining conditions for a week. See? And it's going to be a cosine rain. No big deal, right? So rain just the first part of the cosine, right? So this has to do with the undisturbed cross-section. I don't know why Steben put these numbers, 0.3. So this is before it started raining. Then it started raining. Do I have this right? Yeah, so at time 0, this is 1, 1 minus 1, right? Everything was constant. So it started raining, right? So the rain is going to last for a week, so cosine just goes like this. It's just part of the period of the cosine, okay, half the period. So it's going to rain for a week, and then it's going to stop. And this is wrong. This is 7. Sorry, right? Then it stops raining. And this we can put equal. It doesn't really matter. So it stops raining. So that means that here, the level of the river is going to grow, and it's going to generate a wave, okay? So what is really interesting, and I'm going to say it here, it's not here in the notes, is this, that we're solving now, I said the wave equation, but now it's not a wave equation like this. Actually, it's Berger's equation. It's a nonlinear case, okay? So there's going to be a wave, and there's going to be wave breaking, right? You've seen, I mentioned this last time, that Berger's, and I just indicated here, can form a shock, which means there's a step, blah, blah. I'm not going to do all the details because this is not really a PDEs course in the theory. But if you have doubts, ask me. I can show you where to read. But I think you're already seeing these things in the master's course here? Yeah? Okay, good. So look at this. So this solution will eventually, right? It would start raining. There will be a wave that will go down. And eventually, the solution will be like this. Okay? This wave, due to the raining, this guy will start rising. And you can see this in the computer. It's very simple to program this, right? As simple as what you're programming right now. I'm not asking you to do it, but you can play with it. So it's going to grow here, the surface, and it will propagate that way, right? And then eventually, it will break because of Berger's equation. And when it breaks, you're going to see a solution which is basically like this. I'm just indicating because you cannot see 2 points, 2 values at the same node point, right? So it's basically, it's a jump in our understanding, but it's really in the computer. It's just 2 big values, one close to the other, right? Like, I mean, a discrepancy of values. Okay, so yeah, this drawing is not very good, but anyway, let me put just a theoretical one like this. So then, look what will happen. I'm sorry. Look what will happen, the difference of these two methods here. Right? This one, the method that actually will do the good job, of course, is this one, right? Or else I wouldn't be showing this slightly more, a little more different. This one, which is the upwind, we already know that it has a little bit of a apparent diffusion, because I showed you last time. And actually, the upwind, in this case, will not conserve mass, basically because of its dissipative mechanism, you can think of it. Even though here it's slightly more complicated because we have this discontinuity. And what is very interesting is that this one, the one written like this, in conservative form, is the one that's better. And what happens is this. Let me call this like this. Right? And basically you can show this one using some sort of a telescopic cancellation, if you put it in times, that this one will conserve mass. And the reason is that the shock speed will be wrong for this one. This one has sort of a delay, and therefore it sort of has this mass that's wrong. Somehow you can think of, without me doing all the details, that this mass here is due to the sort of a dissipative mechanism. Okay? So usually for shocks, and I'm not going to do much, one could do just a big chunk of this course just doing shock capturing methods for PDEs, right? And this is something, for example, that people who do flow in porous media here at IMPA, like Dan Marquezin and Alexei does some, now he's more into turbulence. These are very important. So I might mention at the end, might give you maybe something to read at the end, and there's many methods specialized for shock capturing methods, right? And Lachs, Friedrichs, Lachs, and then there's Eno. So there's a method that's called Eno. I think I mentioned this, right? There's like methods that are called like this. Eno is essentially non-oscillatory methods, which so that the solution doesn't oscillate under shock like you see the dispersive run. And this is weighted, essentially non-oscillatory. Anyway, there's a lot of stuff on this, sophisticated stuff on shock capturing methods. But this is a very simple way to show to you that little differences, little things in your formulation, when you have a weak solution as opposed to a classical solutions, certain things can go wrong. Here is not that dramatic, but in particular, if this is a flood wave, if there's one thing you wanna capture right is the arrival time of that flood wave to sort of evacuate, say, things and so on. Okay, so this is the comment I wanted to make at this part. Now let me mention another method, another class of methods for waves, which uses, you can call it, one way to call it is Lagrangian method, semi-Lagrangian method, or Eulerian Lagrangian method, and I'm going to give it to you with this still very simple equation, okay? And actually, these semi-Lagrangian methods are methods used, at least as I know, in many, and even here in Brazil, weather prediction systems, models, okay? Even though we're not going to see complicated PDEs, but let me show you the idea, okay? So the idea is like this. It's using the characteristics, right? So as we saw, the method characteristics, right? If we have basically amounts to so we basically somehow rewrite this PDE in something that looks like a system of ODEs, but it's not a system of ODEs, right? It's like, it's an infinite dimensional system of ODEs in theory, but in practice, for numerics, it's going to look like a system of ODEs, right? So we know in this case, so if the initial condition is this, right? We know that the solution is like that. Okay? So numerically, we can think now of the following. So here's our grid. So look at this. In this problem here, or for this solution here, in theory, what I have is this. Since I use the characteristics as my color notation in orange, right? I have that over these lines here, the solution, right? These are the characteristics. Over these lines, the solution is not changing, right? So basically, I could almost think of having a grid like this, okay? So that means the solution here is the same as the solution there, right? So I can think, in some sense, that if I'm on a moving frame, or almost like in this case, following a particle of the wave, so that thing is not changing there, right? Because if we think of this as a tracer on being transported by you, that tracer is not changing. If it's the tracer in the sense, concentration of a pollutant, for example, right? So therefore, we can now think that, okay, let's work now with two grids. So that's why it's called sometimes or this is the name actually most used. So let me put this one in parentheses because this one's more used. Semi-Lagrangian method or Eulerian Lagrangian method, because I'm going to think of an Eulerian grid. Eulerian grid, those of you who have done fluids already know what I'm talking about. Those of you who have not done fluids, no big deal. Eulerian grid just means the usual grid we're looking at, this fixed grid. So I'm going to stand on the point X, J, and at time Tn, I'm going to be checking what's coming by through this point, this observation station, okay? And somebody else could be at another grid point, like Marcio, xj minus 1, and checking what's passing by there. So the Lagrangian one is a little more like the formulation of it's more like the characteristic method. You're going to follow things. So if we follow things, okay, and I don't have this x and delta x, delta t exactly equal to u. So note that if I have delta x equal to delta t. Sorry, it's a jet lag effect. So if I have delta x over delta t exactly equal to u, if I have the numerical speed exactly equal to the theoretical speed, basically, in the method of characteristics, say nothing happens. The dynamics is silly. It's just the value is constant over this orange line. Okay? Now, so if I do a method inspired by that, and if I have, let me draw this like this because I'm gonna erase it, okay? If I have, excuse me, maybe let me get some of these things that help. If I have then delta x over delta t equal to u, the characteristic goes through exactly through the nodes of my grid. Okay? So I have to do nothing. I just have to transfer the value from here to there, and that's the solution. But in general, in particular in more complicated PDEs, and blah, 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 or like numerical weather prediction and so on, you don't know these things beforehand. So let's pretend that we don't know that. Okay? So if I don't know that, let me do a drawing just like in the notes. Let me, whoops. Let's pretend that I don't know which delta x and delta t to choose, and I have not chosen the one that matches the speed u. Okay? And in this problem, we know that the characteristics are straight lines. But you can already think, and it's healthy to do that, and for example, in an atmospheric flow problem, in a more complicated problem, the characteristic does not have to be a straight line, but in one time step, we're going to approximate it by a straight line, right? So in orbit, even though it's complicated, if the time step is small and this orbit is continuous over a little chunk of time, it's well approximated by a straight line, okay? But then, and particularly in this case where the orbit, the characteristic is a curved thing, there's no way I can pick a delta t and a delta x where it's going to always hit the nodes. That's why this exercise is good, right? So how do I solve numerically a problem with these two ingredients of a fixed grid, but also something that's like a trajectory, a moving particle, whatever you want to think? That's the semi-Lagrangian method, which means semi doesn't mean half, but partially Lagrangian, right? Which is, I think people use this jargon because it's easier to say, but it's basically Eulerian Lagrangian. You put the two ingredients together, and it's very simple and very interesting and useful in some situations. So, okay, so now let me use the jargon that's commonly used in atmospheric flows. The node of my grid, I'm going to call this the arrival point. Okay, this is for the A. And this one, the departure point. So for this problem, let's not complicate things before we fully understand the problem, okay? So let's go back thinking about the silly, simple, unidirectional wave equation, okay? If I know the value of my solution at the point D, I know how to do the evolution. I just transfer this value to the node j n plus 1, and I'm done. Do you agree? Just a transport. The problem, which is not a big deal, it's not really a serious problem, is that the point D, the departure point of information, does not follow my grid. So what would I do? Help me. It's very simple. What's the intuition say? No, you can't change the grid because the grid is fixed, as I said. Remember, for this problem, I could have changed the grid, but we also have to think, but I mean, you can't change the grid because if you have an orbit that's not a straight line, right, the departure point is going to be, can sometimes even fall on the grid, can fall in between grid points, and can fall at different spots in between grid points. So I have to be prepared for that. Choose the close points. That's getting warmer, that's getting better, and do what? When you say choose the close point, okay, my drawing, let's suppose this is the close point. What do I do with that? See, we're doing a very good exercise now, simple of numerical method designing, right? That's what we're doing. So keep on going. Help Márcio say something else. Choose the nearby point and do what with this nearby point? First of all, you understand what I want, right? I want to learn what the value in D is, the departure point, and just transfer it to the node point because I know along this orbit things are constant. So, okay. Huh? To connect this to that? No, but to connect, you mean to what? To transfer this value over there? Connect, I don't understand what you mean by connect. See? When you say connect, what I imagine is transfer this value over here. Because this value here should be more or less close to this value here. That sounded a little bit like what Márcio was saying. You just said it with different words. And Márcio didn't fully complete, right? So I might be wrong, but that's what I imagined that you were thinking. So you might correct me if it's wrong. I can do better than that. Come on, ideas. So again, you understand, right? I want to put assign a value here. I want to update my solution from this level to this level, which means I have to find a value for my solution here. I know that the value of my solution here theoretically comes from the value of the solution here. But the value of the solution here is outside my grid. So at time n, I already know, let me put it like this, my values at the crosses. This is done. So what should I do next? You can take the mean, very good. There's a better word than for taking the mean, which makes us already gives us a little more of a generic insight of what will be done. But yes, take the average. The word better than the average is interpolate. Huh? Interpolation. Do an interpolation, right? So if you do an interpolation with these two grid points here, it's like an average, right? But then I'll mention this. So actually, if you take, so let me say a few things. Let me see in which order I say. Okay. Some people, someone say the average is good. Some people would at first say, oh, since I am on this cell, right? And this guy belongs there. So some people would think first, oh, take these 2 points here, do a polynomial approximation, which at some point a polynomial approximation could be like an average, and extrapolate to find this guy. It's nearby. But it's extrapolation and polynomial approximation not always very good. Okay? So you guys already went to the right direction, which is if this point is here, take the average of these 2 points. Okay? So options is for the departure point is polynomial interpolation, okay? Which as option 1 could be a linear interpolation, which means these two nodes here. Let me put it like this. And if you do linear interpolation, it gives you a little bit of numerical diffusion or attenuation, like the upwind. So numerical interpolation usually implies some numerical diffusion. So the recommendation is usually, right, to use cubic interpolation. Which is these points, which implies to some small dispersion, numerical dispersion, but it's better. I'm not proving this. I mean, we're not going to go into the details here because or else I got to move on and so on, but at least you learn some things. Soon I'm going to do a little bit of numerical analysis, simple. But this is what happens, okay? So if you have a speed that actually gets you out of the cell, you should not do extrapolation. Bless you. So, for example, if you've chosen a cell, this is a comment I forgot, and I just remember. If you've chosen a cell, okay, and so if you have a situation like this, okay, you understand what I'm saying, right? It's a cell where the departure point fell inside the same cell, okay? And you do a linear interpolation. It's pretty much the same as doing the upwind in terms of diffusion and so on, right? If it falls outside the cell, okay, this means that the numerical speed is smaller than the true speed, because the true speed is making it go several cells further. So extrapolation might lead you to some instability, particularly depending on the ratios. And the recommendation is that you use cubic interpolation, okay? So how would we do this, numerically speaking? Numerically speaking is like this. Right? Look, this is an approximation of what? Of this ODE, very simple. So for us to find, it's basically because it's linear, right? It's a linear slope. This gives us the departure point. The departure point is the xj coming backwards, right? And then after you have that, basically you have the numerical method in a quick way is this. So a simple way to writing the algorithm is like that. See if you agree. The departure point is just given by this simple slope, is xj minus that, right? Then I found this point, and then the node would be updated according to the solution at that point. What is hidden in this notation is what kind of interpolation I'm doing to find this guy, right? Do you agree? So here's a very simple way to sort of say what the numerical method is doing. And if we use, right, so here's in the notes, if we use Lagrangian, cubic Lagrangian interpolation, So let's see if you understand what I'm writing. This is the cubic. So here, instead of Lagrangian, I think it's better to say, or else it makes, I was going to call attention, it's Lagrange coming in two different ways. It's Lagrange polynomial, and the other one is Lagrangian dynamics, right? So I got carried away. So this, right, has, excuse me, other terms that looks exactly like this. This is that the Lagrange polynomial, which behaves like a Kronecker delta, right? It's going to be a node 1 and 0 on the other ones. Everybody knows what I'm talking about, right? And therefore, this is the good one for this guy, and so on. So if you like this and you want to see more details, I'm going to write, which is more details. For example, there's nice papers on this. And for atmospheric flows, there's this paper here, which I'll make other comments. This paper here even goes beyond of what I'm saying. And it's by two researchers in atmospheric flows. So let me read it for because I'm abbreviating. It's in the notes, more detail. So this is a paper by Rausch and Williamson. SISC is an abbreviation for SciAm. So this is 4am, SciAm Scientific Computing. SciAm has 18 journals, different journals. Right? This is 1990, SciAm Scientific Computing Journal. Two researchers related to atmospheric flows, and they say, on the shape preserving, I'll tell you what this means, interpolation, and semi-Lagrangian transport. So what I did here is a very sort of introductory beginning for this type of way of doing numerical methods. So semi-Lagrangian transport, you already have an idea here. But actually, if I remember, this paper starts with, I think, maybe the wave equation, mentioning things. And shape preserving has to do with, the name shape preserving comes in different flavors in numerical methods of our interest. One is here. So there are numerical methods for shock capturing that mentions shape preserving methods. So the WeKnow and the eKnow, some of them have to do with that, is that they want to avoid oscillations. So that means they want to somehow preserve the shape. This is a little more shape preserving on its own. Right? And sometimes there are methods too that the oscillation comes down and does this. Okay, this is a bad drawing, but just to indicate. And if you're talking about, say, the transport of the concentration of a pollutant, a negative value of a pollutant is unphysical of a concentration, right? So shape preserving methods, also in that spirit over there, is a method that controls a little bit oscillations, controls if the solution does not become negative, and this and that because of its physical meaning. And sometimes this is done by adding, for example, constraints on the transport, constraints on derivatives and so on, right? They have different flavors. So this is what is meant by shape preserving. So I wanted just to share with you one of many, and this already has some time, references for people doing research and things much more complicated with it than this, but this with the ingredients we are seeing, okay? Which is semi-Lagrangian and shape preserving. And the thing is that if you do semi-Lagrangian, for example, for this wave equation, okay, so if you do this equation here, and you do semi-Lagrangian, and always sort of interpolating and not extrapolating and so on, you don't have the stability issues that we saw before with the modified equation. So there are some things that, that are advantages and stuff like that. Okay? So this is one thing I wanted to mention. Okay. Good. I have a little bit of time. My voice is still here. So let me do at least. Now let's do a little check, which we haven't done, which is a stability condition for the diffusion equation we did. Remember that I mentioned the advection diffusion equation. So the advection diffusion equation had the transport part, which is this, and here on the right-hand side, the heat part, right? And I mentioned to you that actually, for this guy here, a good discretization is dx dt, that is dx over dt, or better. This gave us no diffusion, right? This is part of the exercise actually we're doing. But when I add diffusion here, now I'm not looking at the numerical diffusion. I'm looking at the physical diffusion. I have to pay attention to my discretization stronger than for this case. And this is what we're going to see now. Okay? So explicit diffusion which means I have this equation and I have this numerical method. Okay. So the question now is, what is the restriction for delta x, delta t? Okay. So I'm going to have the wave number which will be 2 pi over L k tilde. K tilde could be 1, 2, and so on, right? Because I'm rescaling on my interval 0 to L. Okay, with boundary with conditions, I have to write this, sorry. Okay, so for our problem, okay, if it was just a heat equation, I'm putting the temperature, right, the heat equation, on the extremes equal to 0 all the time, right? If it's our advection diffusion problem with the pollutant, remember the one that had the chimney with the pollutant, I am saying that 0 and L are far away so that during the time that I'm studying the problem, there's no pollution there, right? So the chimney would be in the middle, the house would be in the middle, and we want to see where the pollution is going to go. But at the extremes, right, I can put these periodic boundary conditions, which we do this many times, particularly when we use spectral methods. I'm going to mention about spectral methods later on in the course. I just put the boundary conditions far away so there's nothing happening in the beginning or during my study, right? So no pollution here, okay? Simple. And then I gotta say, I want to see, well, let me try to get some insight now of what are the implications, in particular of this, right? I have delta x squared and delta t. So this is not really a stiff problem, I wouldn't say, but it puts more constraints on my meshing, which is my mesh size, than the wave equation. And this is what we're about to check now mathematically. Okay? Understand the goal of our exercise? So the nice thing to do here is to do, which we can do this many times, is to do a discrete Fourier analysis of the method. I mean, of the method I didn't even have to mention, but it's a discrete Fourier analysis, right? Because, look, I have basically here a discrete dynamical system, right? Explicit in time. It's a discrete dynamical system that will evolve my solution. And, well, I'm already on a finite interval and so on. So even if I was doing this for the equation, it's a Fourier series, right? So it's Fourier series is already discrete as compared to a Fourier transform. But here, for this method, I can study it in a very simple way using a generic Fourier mode. Okay? So here's my Fourier mode. Okay, so look, it's a Fourier mode. It's like a little bit like a separation of variables. This guy here takes care of the boundary conditions, right? That's why I do a sine Fourier mode or a sine Fourier series, if you like. But the problem is linear, constant coefficient. So I just need to check a generic mode for some generic k. And then I understand everything due to superposition, right? It's a linear problem. So I'm going to say then that my discrete concentration at point xj time tn is basically has an amplitude, which I'm just going to call it an, but don't forget that it depends on the mode. And here's the mode, the spatial distribution. No big deal, right? It's a Fourier analysis of this guy, okay? These things sometimes are messy. I mean, there's all details in the note. I'm going to skip some points, but not much. So substitute here, right? And we're going to get something that looks like this. Okay, I'm already abbreviating to save us time, right? So, no, there's something missing? Yes. Right? So this is becoming, see, when I use the Fourier in space, this is becoming like a discrete ODE for the amplitude. Just like when we do, say, if we did a separation of variables, right? What am I lazy to write here is just xj minus delta x. Okay? Right? And what would you be dying to do now? And I'll skip some of the parts because it's just trigonometric algebra, right? But what do I want to do here? Right? So look, all I did is substitute this in here. Okay, so this guy came over here. That's what I got. This guy stayed over here. Boom, boom. Okay? And what I'm dying to do now, and you should be wanting the same thing as me, is to clean up as much as I can the spatial part of the problem because this looks like an ODE, a discrete ODE for the amplitude, just like when we do a Fourier analysis for the continuum part. So therefore, right, I'm going to skip. Therefore, I'm going to use the trigonometric relations for sine of A plus B, sine of A minus B. Try to get the sine of KXJ out and cancel it. Clean it up, and I'm going to give you the result now, right? I'm going to write this in between. So this happens to be something like this. Okay, so please make sure that every time I write the kappa for the diffusion coefficient, I'm making this k with a little lace here, okay? So that don't get confused with the wave number. So here we have, right, so look at this. We're back to something that looks like it is not, but it looks like the absolute stability problem, because this is the amplification factor. Do you agree? It's like the propagator, right? This is the amplification factor. It takes me from step n to n plus 1. And amplification factor is, as we know in mathematics, is a little bit an abuse of the colloquial term, meaning amplification factor if it's greater than 1, but actually sometimes it's a contraction factor if it's smaller than 1, right? And we know in the diffusion problem, if something's growing, and it's an instability, right? In this case, we want the coefficient to decay in time. We saw this through what? Through the dispersion relation that I did some classes ago, okay? So the amplification factor, I basically can write it like this. Let's see if you agree. So for numerical stability, I should ask for this, right? Because look, right, if I keep on coming back, I'm going to get this guy to the power n, right? Just like we did before, depending on A0, which is the initial amplitude, right? Just like when we did for the absolute stability problem, the test problem, okay? So for this solution to decay, I need that this number, an absolute value, be smaller than 1. Here it is. And the only thing that was done is we rewrote this, just maybe make life simple, as this, and we got to factor because of half, it becomes this. It's just trigonometry, okay? So then we need that this guy be greater than minus 1, smaller than 1. This guy here is real, so this guy here is always going to be smaller or equal to 1, right? So we basically controlling this and that, we get, so this, let me see if I can write it here, right? We get, basically we get this guy here to be smaller than 2, right? Because if it's 2 would be then 1, so on. And this, from here we get this. Okay, so if we have that delta t is smaller than delta x squared over 2 kappa, this is satisfied. And then you see that diffusion imposes a stronger restriction than transport, right? In transport, look, it's good that I have this here. So see, in the transport part, if you tell me, oh, André, this is an x. André, you know what? The solution is not, well, I'm not seeing the solution with a very good resolution in delta x. Maybe I have to put more points. I have to divide delta x by 2 so that I can see a nice solution. If I do that, what do I have to do in time? Divide by 2. And then I keep the same courant number, right? In the heat equation, no. For the heat part, no. If I decide that, you know, I need a better, I want to see my solution nicer, it's a little bit, I have to divide delta x. I have to refine my grid and divide delta x by 2. This will mean I have to restrict my delta t by even more than 2, by 4. So it's more restrictive. Okay, this is not, it's different from the case of stiffness, right? But it's more restrictive. Okay. So let me see, maybe my voice, I'm getting a little tired too. Let me just prepare what I'm going to do for next time, okay? So for the transport part, okay, for the transport part, we've seen many things that can be done. I was not exhaustive, right? We didn't see in all detail, but if you have transport and you have a shock, that's just a whole new story, and could be a specialized part of the course, which we're not going to do, at least. Maybe who knows a little bit of it in reading. We'll see at the end of the course. If we have, depending on the problem, we might choose another strategy, which is semi-Lagrangian. We can also do spectral, and we'll see what aliasing means. That part I will do, okay, in the course, using Fourier and understanding, you know, what aliasing is and so on. Okay, and now there's the diffusion part, but that we saw that we have a stronger restriction. So next class, I want to mention 2 things, okay? So let me just sketch here very quickly. The first thing is that I think I already mentioned here in the course, but this is a center difference, right? We can get the center difference. Excuse me. I gotta write this. Cannot be lazy because this is important. Excuse me. So you see, this center difference can be obtained excuse me, by the forward and the backward the forward and the backward Taylor expansion, and by just adding it, right? So if I add this guy kills this guy, boom, 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 and I get an approximation for the second derivative. Okay? Easy. Now, next class, I will talk about the method of Crank-Nicholson, which basically the heat equation is written like this. And then I'll stop here. That's all here, but I want to leave one thing in the back of your minds. This is good, like little, well, we have an expression in Portuguese that makes no sense in English. In English would be worms in your head, minhoca na cabeça, right? So it doesn't make no sense in English, but keep you thinking, right? So this is Crank-Nicholson, okay? Basically, preparing to finish the class for next time. So what have I done here? And what does this remind you? Let's see if I wrote things well. I forgot. Yeah, I think I have it right. So, what have I done here in words? I mean, not me. What have Crank and Nicholson, this is not Jack Nicholson, some other Nicholson, what have they done here? Simple, very good, by the way. And you might even use words from what we saw in numerical OD. Trapezoidal rule, right? Just, this is 1/2. You can put this here. Put here is 1/2 of the right-hand side. Right? So it's implicit now. It's implicit. It got the second derivative at time n plus 1, the second derivative time n, and did an average. Okay? By the way, there's something in PDEs that's called, I will mention this at some time, but if you have a problem like this, look, okay, if you have this problem, and then you do a semi-discretization, it's called the method of lines. And sometimes you might see somebody talking about mole. It has nothing to do with chemistry, right? It's method of lines. Semi-discretization method of lines is this. Is this, you do a discretization, okay? And it's like you do this. What you have here. Here's the matrix, see, with a tridiagonal form. Right? So this is the method of lines. And then you can look at the eigenvalues and so on. So this is the method of lines. And therefore, the trapezoidal rule is exactly for this part. Okay, as t n plus 1 and t n. Okay? And what I will convince you next time is that the first thing is already good, okay? Recognizing that this is basically the trapezoidal rule, it's good, and we saw the trapezoidal rule was good for oscillations and stuff like that, and right? So, okay, but this is just diffusion. There's no oscillation. A wave problem, yes. But what is interesting here is that this, and I'll show you this next time, that this is equivalent of doing this. So you see, when we center things, okay, what I was showing to you is that when we center things, when you have centered differencing, usually you kill terms using the symmetry. So you see, when I had this went forward, this went backward, this is centered at J, and I killed this guy, and actually I will kill this guy too. Okay, so usually when you center things, you will gain accuracy. This guy here at first looks like what method in time if I think of it as an ODE. Forgetting about this, it looks a little bit like just an Euler kind of method in time. But when we do these tricks here of the trapezoidal rule on the right-hand side, we will see that this is the same as doing the PDE. And when we look at the molecule, it's like the PDE evaluated at the half-time. Right? And that's good. So we'll see this next time. It's simple, but just looking at Taylor's series, we can see that. Well, I thought I was going to end up earlier a little bit today because I'm tired, but actually, this is more or less the right time. So, okay, thank you. Obrigado.